All right, here we go with our first no microphone recording. I'm nervous. After wasting 18 minutes and coming in late to begin with because of the previous class. All right, so we answered a few questions during the break. Why don't I go ahead and get lecturing so you get something out of this rather than frustration on microphone stuff. All right, you guys can hear me all right in the back? All right. So what I want to do is I want to briefly talk about how to bias with the resistor and all that stuff. So has everybody been reading the book? Easy to read? It's a loaded question, right? So I want to talk about the biasing. Okay, so if we have a resistor like this going to VDD and R, we went over this last time, man, it's a lot nicer without that headset on. Hope this works. Would everybody agree that if that's the case, if VDD changes, it's going to directly change the VGS here? That's pretty straightforward, right? Okay, so what we want to do is we want to somehow develop a circuit where instead of putting a resistor in the drain side where it's connected to the power supply, we put it in the source side to try to make the current independent of the power supply voltage, okay? So the way I'm going to approach that is I'm going to do the following. I'm going to go through this nice and slow. I'm going to make a current mirror. It looks like this. However, instead of grounding this side, what I'm going to do is I'm going to put a resistor here. Okay, so if I look at this and I ask, all right, if these are the same size devices, does everybody agree that the VGSs would have to be the same if the same current flowing through them? Let's pause. How would I get the same current to flow through those two devices? Well, I want to put a current mirror up here to force the same current through each side. Okay, so let's do that. So we'll put, and I want to pause on all of this. So this is a PMOS current mirror, and its goal in life is to push the same current through each side. Does everybody understand that? Okay, so I've got a question. Why did I put the gate drain connected PMOS over here instead of over here? Nope. If you look, if I put it over here, then I've got VDD equals VSG plus VGS. I could write the loop, right? Because I got a VSG right here. Does everybody follow that? Okay, and then I have a VGS here. And so I'd get VDD equals VSG plus, that's if I put a wire here. That's not good because then VDD changes, it directly changes both VSG and VGS. Does everybody see that? Okay, so I want this node to be able to stay at VGS at a fixed current, and the only way I can do that is if the drain of this transistor, which is right here, is allowed to move around, and it's allowed to move around if I hold its VSG constant, let the drain move, and hold this VGS constant. So when I have one side that's connected like this, I have to have the other side gate drain connected like this. Does everybody follow? Okay. The goal in life for these two transistors is to put the same current through each side. So we'll assume that it is the same current. Neglect the output resistance. Okay? Okay, if I do that, then I ask, all right, well, if I have a VGS here and a VGS here, these are the same size, they have to have the same VGS. If they have to have the same VGS, this voltage obviously is then VGS. And then that voltage is VGS. How much is left to drop? How much pressure is left to drop across this resistor? If I have the same current flowing through each side, this VGS is the same as this VGS. How much voltage can drop across that resistor? Zero. There's no pressure left to drop across that resistor. And the only way that'll work is if I is 0. And that's not useful. So the only time it works is if the current flowing in both sides is 0. Does everybody follow that? Okay. So what I'm going to do in order to avoid that situation is I'm going to reduce the VGS of this transistor. To reduce the VGS of the transistor with the same current flowing through each side, what do I do to the W over L? Yeah, make it bigger, right? If I make it bigger, then I don't need as big a VGS, and then the rest of the VGS1 is dropped across here. So I'm going to write that. I'm going to multiply up the beta. I'm going to make this K times W over L, and this one W over L. Okay, so let me label a few things here. Let's call this M1. We'll call this M2. We'll call this VGS1. So what's this voltage then? VGS1. That was an easy question. Then this voltage here, because this we'll call M2, is VGS2. So if I have VGS1, there's VGS2 here, what's this voltage? VGS1 minus VGS2. Does everybody see that? Okay, so if I had this voltage is VGS1, and then I had some element here, and I said the voltage across that element, whatever it is VGS2, then this voltage is VGS1 minus VGS2. That's what this voltage is right there. Any questions? And it's been so long since I've done a lecture without something on my ears, it feels bizarre. All right, so I'm going to come back to this. So I'm going to go right now. There's my PMOS. They're the same size. This drain isn't gate drain connected, so this drain can move up or down depending on the power supply moving. This drain isn't gate drain connected, so it can move up or down. So as I increase VDD, what happens to this drain ideally? If I drive VDD, say from 4 to 6 volts, what happens? Let's assume, I'll give you a hint, let's assume the ID is ideally constant, because that's the whole point of this, is to bias at a constant current independent of the power supply voltage. So if I have a constant current going through here and I increase VDD, what happens to this voltage? Okay, this is a trick question. If I put a constant current through a gate drain connected device, what happens to VGS? It stays the same. It's like, oh, I got my hose and I'm adjusting the pressure. I want the pressure of water flowing to not change. How do I adjust the valve? Well, I keep the valve the same. Ideally, I get the same water through. So this stays the same. And it's equal to VGS1. Does everybody follow that? Okay, however, if I pull this one up, it's diode below VDD. So what happens to this voltage? Because what does this VSG do if I increase VDD? Same current's flowing through it. Stays the same. So VSG stays the same. So what happens to this voltage as VDD goes up? It goes up. Okay, one more time. If I have a constant current flowing through both sides and I see a gate drain connected transistor, I know that VGS is equal to the square root of 2ID over KP times W over L plus V threshold N, right? Does everybody agree with that? All right, so then I ask, all right, if that's the case, and ID is constant, everything else here is constant. What is VGS? Constant. So if I increase VDD, but I keep the same current flowing through each side, this voltage stays the same, stays constant. If I increase VDD, I keep the same current flowing through both sides, this voltage, VSG, stays the same. What happens to this one? Well, it's VDD minus a constant voltage. I raise VDD, this voltage goes up. everybody follow that? So, if I raise VDD, what happens to the VDS of this transistor, assuming the same current through both sides? It goes up. If I raise VDD, what happens to the VSD of this transistor? Goes up. What happens to the VDS of this transistor? Stays the same, it's gate drain connected. This one stays the same, gate drain connected. Any questions? So what should I label this, M1 or M2? M1, to stay consistent. I flipped it just to mess with your mind a little. Very little, right? And this would be M2. This voltage I would label VGS1. This is one of my favorite quiz and test questions. What is that voltage? VGS1 minus VGS2. Okay, so in terms of this resistor here and the current that's flowing down here, how is this voltage, VGS1 minus VGS2, related to I and R? Anybody not see that? Okay, so I'm going to take this equation. Remember that this one is KW over L times wider than this one. Beta times wider, beta multiplier. And I'm going to put in the equations. I'm going to substitute for the VGS's in here. And what I'm going to get is I'll get the square root of 2I over KP times W over L plus V threshold N minus the square root of 2I divided by Kp times Kw over L plus or minus V threshold N is equal to I times R. What happens to the threshold voltages? Why is that good? What's that? Threshold voltage changes with temperature, cancels out. Threshold voltage changes with process, cancels out. It's not dependent on the threshold voltage, unlike biasing with a resistor or long L transistor, one of those other techniques. Everybody clear? Okay, would you all be okay if I wrote the following, that this is equal to, I'm going to factor out square root of 2I over Kp times W over L, and write this as 1 minus 1 over root K. Is everybody cool with that? Okay, we're almost there. Is this an unreasonable quiz question? Yeah? All right. So I'm going to square both sides. Yeah, let's be verbose here because I want to make sure you can drive this because we'll use this circuit the rest of the semester. 2I over Kp times W over L times 1 minus 1 over root K. And I'm going to pause here because for some reason people have problems solving this. Tell me what to do. Square both sides. One way, divide both sides by square root of I, then square, whatever. So we'll square both sides and we'll write 2I over Kp times W over L times 1 minus 1 over root K squared equals I squared times R squared. Now what? I's cancel. And I get I equals 1 over, and I'm going to rewrite this a little bit, R squared times Kp over 2 times W over L times 1 minus 1 over root K squared. Looking good? All right, let me make sure that's what I wrote in the book. So after class, go watch the video and tell me thumbs up or thumbs down on the audio like this. I already know what the answer is going to be.
I'll make sure I put it on the big screen at my house, so if it's real loud, it bugs everyone.
All right. All right, I don't think I made any mistakes deriving that. Does anybody have any questions? What I'm worried about is the distraction of the audio changing levels. Maybe they've got it set up now that it equalizes or something. Okay, so is this by itself that useful? I mean, I could look at this and let's make some useful comments. Is I dependent on the power supply? No. The only thing I is dependent on is this factor k, which is, say we make it 4. So then what happens if k is 4? This becomes 1 over 2. 1 minus 1/2 is 1/2 squared. Then the 2's cancel, and I get I equals 1 over r squared times kp times w over L. Okay, does everybody follow that? Okay, so I want to just point you to something here real quick that's useful. If I move these up and well, let's move it down. Let's move this down and move the r. We'll leave the r right there. We write I times kp times w over L equals 1 over r squared. Tell me something useful I could do here to get a parameter that we design with. Does everybody see what I did? Just move this up. What could I do that's useful? I'll give you a hint. Let's take the square root of both sides. Yeah, that's GM. So, if I set K equal to 4, I have a specific transconductance I want to design for. I set my resistor to 1 over that transconductance, and that designs my circuit so that I get the transconductance I want. Yes?
Did you have a 2 in the denominator?
Nope. Remember, if K is 4, then that's 1/2, right? Oh, yes, thank you. So it's 1/2 squared, so 2 of the 2's cancel. And of course I need a 2 here for it to work, don't I? Yes, keep me honest. All right, does everybody agree with this? That I can set R with K equal to 4 to 1 over the transconductance. Looking good? Let's take it a step further, because we can also get one other useful thing with this, and then we'll do some sims, and then we'll talk about some designs. Let's go back to this equation. Let's just write this GM here, or let's go back even further. Let's go back to right here, and let's derive something else useful here. So let's write I is equal to 1 over r squared times kp over 2 times w over L. And let's just leave it like this for now. No, let's go ahead and write it as 1 minus 1 over root k. Okay, what can I write I as, though? Oops, I left out a square, didn't I? What can I write I as? I'll give you a hint. Kp times W over L divided by 2 times VGS minus V threshold N squared is equal to 1 over R squared Kp over 2 W over L times 1 minus 1 over root k squared. Yay? All right. So what happens when I square both sides? Let's move this being up here, and we can write that as r over 2 times kp times w over L times VGS minus V threshold N squared is equal to 1 minus 1 over root K squared. Whoops, not squared. Looking good? All right, so if I make this k equal 2 again, or k equal 4 again, what does this term reduce to? 1/2. The halves cancel, and I get kp times w over L VGS minus V threshold N is equal to 1 over R. Did everybody agree? And what is this? Yeah, GM. Well, you just derived it a different way. And what's another name for this? VDS sat or V overdrive for a long channel. Is everybody cool with that? Okay, so let's go and look at our general design was at table 9.1. What page is that? Yeah, table 9.1. Remember, we set these device sizes based upon speed and open circuit gain and all that. And we made it L2 instead of 1, so we get a little bit more gain, a little less speed. This is good for general analog design. We set the overdrive to 5% of VDD for 250 millivolts, and we set the bias current to 20 microamps. So I want to go through and set the parameters now and show you how to bias so that you're in this table. Okay? So I want to sketch the schematic of a beta multiplier. So can you all remember NMOS is 10 by 2, PMOS 30 by 2, and the VDSs and all that? Okay, and then we're going to use, and what's our GM? Not that we need it at this point. 150. If we set the ID to 20 microamps and the overdrive to 250, we basically only need this and this, and we'll see how it simulates. And then we're going to do a dot operating point on that. So here we go. I've got my PMOS. So this is when you start an analog circuit, you have to design a bias circuit first. And you don't want the bias circuit to be temperature or voltage dependent. You want it to be steady. You don't want the sound to change as it gets heated up. So let's go like this. So what do I label these sizes for that particular process? 30 by 2. And then I come over here, and then I go, okay, this one is 10 by 2. Come over here. Okay, the beta multiplier is 4, right? It's multiplied up by 4, so what do I set this guy's size to? 40 by 2. And then I need to set the resistance. Now I could go directly and say, oh, the resistance here is 1 over GM, which is 1 over 150 micro, which is 6.5K. I could stop right there, and I know that I've set all the currents and everything in this circuit just based on the GM alone. Or I could go back and solve for the R, knowing that 1 over R is equal to, for this, 120 microamps times 10 over 2 times 1.05 minus 0.8. Now I'll give the same exact answer, because what is this? GM. I'm setting GM to 1 over R. So does everybody see how I did this design? Okay, so I want to simulate it. So before I do, what I expect to see is I expect to see changing 0 to VDD and the current staying approximately 20 microamps. If the transistors were perfect transistors, that's what I would see. In reality, what I'm going to see is I'm not going to see anything happening until I get to a voltage which is roughly, let me calculate what the minimum VDD is. This is a good test question. VDD. So I need a minimum voltage across here. Let's assume everything's operating correctly. What's the voltage here? Okay, this is, you need to get used to this. You have the table, you have the calculations. This is easy part. So what's the voltage between here and here for the PMOS out of table 9.1? 1.15. What's this voltage? 1.05. What's the minimum VSD sat I need for the PMOS? 0.25. It's VSG minus V threshold P. So I need 0.25. Does everybody see that? What voltage do I need this to be? .05. So if I ask you, what's the minimum voltage that I need for VDD for this circuit to work? About 1.2, it's going to start turning on, right? So I should see basically no current then at about 1 volt or so. It should start going up, and then it should level out and say from 2 volts to 6 volts, and maybe it won't go as high as 6 volts before something breaks down. I should see it staying flat at 20 microamps. And this is VDD being swept. In other words, I have a circuit here that doesn't change the bias conditions as I change VDD. Is everybody cool with that? So let's sim it. Any questions? Okay, so let's look at figure 2016. Wait, before I do that, 30 by 2, 30 by 2, 10 by 2, 40 by 2, 6.5K, 30 by 2. So 2016, figure 20, why don't I have 2016?
It's down.
A little higher. Top was great.
Wait, why? That's bizarre. It must not be sorted by name. What? Whatever.
You're missing an underscore between.
Oh, is that what it is? Because these are symbol.
Figure, yeah, see an
There's no
underscore.
space on figure and point.
Oh, I see. All right, yeah, I probably did that because these are symbols. I use those as sub-circuits. All right, 2016. Okay, forget this for a moment. I'll talk about this in 2 seconds. This is the circuit we just talked about. 10 by 2, 30 by 2, 30 by 2, 40 by 2, 6.5K. Then I put a temperature coefficient here for the resistor so it change. So I'm going to sweep VDD from 0 to 6. We set it about 1.2 volts or so. It would start to turn on, so we can run it. And we see it starts to turn on 1 volt or so, starts cranking up the current about 1.3 where we calculate 1.2, 1.3, it starts flattening out. And then why is it not perfectly flat with changes in VDD? Why does it just go up approximately to 20 and then not stay flat? Yeah, the output resistance of the transistors. As I change the voltage across the devices, they're not perfect. They're going to have some variation as you increase the VDS. So when I go look at this, and I've changed the VDS across here, because this point ideally stays at 1.05, the current in this side is going to go up. Does everybody follow that? So at high voltages, which side do you think is going to have more current? This side or this side? And why? This current or this current? And why? This side will have more. Why? No. What's the VSD across this transistor? It's bigger, right? As I increase VDD, the VSD starts to grow. This one, it doesn't. It stays relatively fixed at 1.05. So the VSD of this isn't going up. This one, it is. So they have the exact same VGSs, so this one I'm moving further and further out on the curve. So I expect the current through this side, through M1, to be higher at high voltages than M2. So let's look. M1, higher at high voltages. At low voltages, it's lower because VSD is less. Did anybody follow that? Jonathan, did you follow it? Liar? Okay. You got me to say liar, and then you said no. Okay. So let's go through that one more time. Would you agree, let's say at 5 volts, that this VSG ideally is going to stay at 1.15? So then this voltage here would ideally, when VDD is 5 volts, be 3.85. This one, however, will be at 1.05. So the VSD across this device is 5 minus 1.05, or 3.95. And the VSD across this device is 1.15. It's 5 minus 3.85, just the VSG. So if I look at the curve, what I've got, both of them have exactly the same VGS, so they have to be on the same curve. But that right side, this side, the VSG is fixed here roughly at 1.15. So this voltage at 5 volts is 3.85. And this one, however, this voltage is 1.05, so its VSD here is 3.85. It's 5 minus 1.05 because of the gate drain. So for this side, I'm way out here. So I expect there to be more current on this side than there is on this side. Does that make sense? Okay, so if I were to ask you, what could I do to increase the flatness of the curve? And you can try this on your own time. How would I make this curve even flatter? I mean, there's tricks we're going to learn in the next lecture, maybe the one after that, called cascoding. That'll help out. But how would I make it just based upon what I have here? How do I increase the output resistance of the transistor? I could decrease the current, but okay, if I do that, then I slow down my circuits, gain goes up, and or what else could I do? Increase the length, but again, what happens? Gain goes up, speed goes down. Okay, so there's trade-offs. All right, I want to talk about this circuit, but before I do, does anybody understand this one? Sarda?
I have a question. You said originally that the point was to drive the same current through it.
Yeah, ideally, if you look at the currents, they're close to being the same, right? But because there's different output resistances, they're a little different. So, but when we analyze it, it doesn't become practical if we start putting the lambdas in for each device and it becomes academic. Basically, what we want to do, we want to design a circuit so that it works and does what we need it to do, all right? So that's what we're doing, but we know it's not going to be precise. But when you look at it, when I look at this circuit, even in industry, I go, same current through each of these branches. I don't think, oh, well, unless I'm thinking in depth, why don't they match? I don't think, oh, this one's a little different than this. I just say same current, and then I do the analysis like I showed here. Everybody follow. Okay, so let's talk, any questions? Okay, let's talk about this circuit right here and what it does. Okay, and there's one other thing we need to do. We need to talk about instability and what happens here. When you go design this circuit, everybody focuses on this part of the circuit when you get in industry, and this part, because you'll see after the circuit starts up and is working, it doesn't do anything. And then all the problems in the biasing end up coming from the startup circuit. So it's very important that it works, and then once it works, you don't need to care about it, all right? But it's got to work, so don't neglect it. Okay, so if I go back and I look at the circuit, this is called a beta multiplier. And I'm really curious if this works, because if it does, good times. It's an example of, I'm going to give this really smart technology so that the user has less control. And that's so smart it doesn't let me use the microphone I want to use. It makes me use this one. Yeah. Alright. So why did I put K there? Because K times wider. That's the beta of this one's multiplied up. Yay? Okay, so if the ideal situation I have, let's just use the numbers from table 1.9.1. This voltage is 1.05, this is plus 5, this is 3.85. What's the voltage here? 1.15. And what's the voltage here? 3.85. I'm the king of the same questions. And then what are the currents flowing in each side? Table 9.1. 20. Okay, this is where I want to operate, and life is good. Does everybody see that? These voltages are the same, these are the same, the current's flowing through here. However, when you power this circuit up, it's possible for it to power up where this voltage is 5 volts, this voltage is 5 volts, and this voltage is 0 volts. If it does, how much current flows if the VSG here is 0 and the VGS here is 0? 0 current, right? And I don't want that state. So there's two possible states. There's the desired state, and then there's the state where it doesn't start up and it stays in 0 current. And if you recall, if you took 421 last semester, we did the band gap reference in the projects. Band gap reference is also a self-biased reference, and it also has a startup circuit to ensure that it doesn't start up in the 0 current state. Everybody follow that? So what I need is a circuit that leaks, that detects this and leaks a little current into some node in here to get it to snap and start up, because there's positive feedback. Once it starts moving, it's going to snap to the other state. So here's how I'm going to do it. I'm going to take a switch. I'm going to tie that switch here to some circuit. I'm going to do something like this. I'm going to make this a long L device. It's not critical. It just needs to drop a voltage, and then I'm going to come over here, and I'm going to mirror this current so I can control the current in this side over here. Whoops. Okay, if I do that, how much before, let's say it's starting up in the bad state, how much current flows in this branch here, and why? Okay, this is, you're using your current mirror knowledge. How much current flows in here? 0. VGS is 0. The gate's a ground. Okay? Does everybody see that? If there's 0 current flowing in here, then ideally, what's this voltage? Well, wait. The VSG of the device is 0. But what's this voltage? 5. Does everybody see that? If this voltage is 5, it pulls the gate of this NMOS up. Pulls the gate of the NMOS up and turns the NMOS on. What does that do? Causes a little current to flow in there, and through this device, which is mirrored over to here, circulates back around. Then this one starts to source current, and then it snaps to the desired state. When it snaps to the desired state, now the current that flows here is 20 microamps, just like everywhere else. Does everybody follow that? Does anybody follow that? One more time. If I have a case where this voltage is at 5 and this is at 0, how much current flows in each side? Nothing. That's not the state I want. So if I'm mirroring across here 0, how much current flows in here? 0. How much current flows in here? 0. So what is the VSG of that if no current's flowing in it? 0. So what's this voltage, the gate voltage? 5. The gate voltage is at 5. What's the NMOS state? It's on, and it leaks current into this gate drain connected. Let's say it puts a microamp here. So I get a microamp flowing through here. Okay? How much current flows in here now? Because this voltage goes up above 0 because I got a current microamp. How much current flows in here? A microamp. It's a mirror. It's a current mirror. That's 1 microamp flowing in here. How much now flows in here instead of 0? 1 microamp. We're using our current mirror knowledge. Well, now I've got a microamp here and a microamp here. What happens? This goes up to 2 microamps. Oh, now it goes to 2 microamps over here, which goes to 2 microamps over here, which goes to 2 microamps over here, which then drives this to 3 microamps, and it keeps going until the current in this reaches the desired state of 20 microamps, which pulls, since this is a long L device, pulls the current through it and drives this node to 0, shutting this device off. Does everybody follow that? That's why there's problems. If you don't design this right, it can leak current into your reference and your circuit won't behave correctly. Does everybody follow that? Yeah, so if I look, let's just focus on this. I designed this, so let's do the 2 states. One is where there's 0 current flowing through here, right? If there's 0 current, this is just a gate drain connected device. It's going to pull the gate up to 5 volts and turn that on to leak current to start this positive feedback process to pull it up, right? Once I get current conducting in here, what I do is I put a huge resistor, which is this big long L device, and then I put a current, because now this is conducting a current, I put a current 20 microamps through there. Okay? So if I put a current through the big resistor, what happens if I make this resistor big enough? What does this voltage go towards? 0. It doesn't have to go all the way to 0 because this voltage is at 1.05. So even if it goes to 1.05, this is VGS is 0. And if it goes to 0.7, then this VGS becomes negative. So I put that big resistor, that long L device, and then that drives this node to 0 because of the current flowing through there and shuts this device off. Yay or nay? Nicholas, yay or nay? All right. Any other questions on why we need a startup circuit? So let's just go back and look. Again, we're going to use these circuits throughout the rest of the semester. When you do your projects, you're going to use it, the beta multiplier. So you look, this one's a little bit different because it's basically shorting these two together so that it pulls this node down and pulls this node up. So it doesn't have to be as, this voltage doesn't have to be as low. Here's our long L device. What's the L? 100 microns. Okay, there's our device mirroring the currents. So if I have 20 microamps flowing in here, 20 microamps flowing in here because the W's wider, how much current flows in here assuming it's in saturation? 20 microamps. It's just a current mirror. You see how you get used to looking at it? These current mirrors are everywhere. They're ubiquitous in analog circuit design. Any questions? I want to cover one more topic here on this. Okay, everybody understands what a startup circuit does. Starts it up. All right, so let's go now and talk about the other, what is this thing? Evernote. Okay, I guess that's for taking notes. Take pictures. Ooh, you know what I could do? Instead of scanning my notes in, I could start hitting this thing. I better play with that. That would be less work for me, wouldn't it? All right, more technology. Okay, so there's one other big problem with this circuit. I want to tell you a practical problem that happened a few years back with a company that was copying circuits from my book instead of understanding what was going on. And even though I said this problem in there, they still didn't, you know, because the book's very, I don't know if you've noticed, but the way I like to write is I like lots of pictures. I like arrows and pointing, and I like looking at pictures. Okay, make your own conclusions about that. And people don't like to look at text, right? They don't like to read. They like looking at pictures. And so people won't read they won't read the text even though there's important stuff in there, okay? You can't put everything in pictures, okay? So they did the following. They built this circuit. and then they connected this to a pad, which is how you get a signal off the chip. You connect it to a pad, and then it goes to a pin of the IC. You know, you've seen the in a print, you know, your op amps or whatever that you use. And the idea was, I'm going to put different resistors here, so I can test my analog circuits with different GMs and different biasing. And you think about it and you go, that's a really cool idea, right? Wrong. And I'll tell you why. One of the issues here with this circuit is that it uses positive feedback, right? So as I showed, I got 1 micron, feeds around. If I add delay in that positive feedback loop, it will cause the circuit to oscillate. So with the capacitance, and if you've taken my lab, you really know this now, or with the pad, there's a capacitance, and there's a stray capacitance associated with the resistor. Okay? When you bond this out, that capacitor adds a delay. And what that delay does is it causes the circuit to become unstable. Because it says, oh, I got a microamp here, and then it feeds back around, and it says, oh, it's too high, and so this voltage goes down. But by the time it can react with that capacitance there, it's gone too far, and it keeps feeding back around the wrong information. And so let me just show you in a simulation. So I went through this. Figure 2024. Does everybody get the basic idea? It's like if, this is a great example, if you're driving a car blindfolded and somebody's telling you directions and you're going slow and someone's, okay, if I go slow I can do it, I can go, you know, turn left, turn right. However, if I speed up or their directions are really slow, there's too much delay, and instead of saying, oh, turn left, they wait 2 hours. By the time I've heard the 2-hour command, you know, turn left, I've already driven off the cliff. It's the same thing here. By the time the information circulates back around the loop, it's old news and it's always trying to fix itself. So let's look at figure 2024, and I'll quickly derive this and then we'll stop. I'll do a quantitative derivation for you. So if you look, we'll cover what this other amplifier is here next time, but I just want to run it and show you. If you look, the current's oscillating. Does everybody see that? So instead of being 10 microamps, I think is what this one's for, it's now 30 microamps, okay? The way you get that fixed is instead of putting, and this is with no extra capacitance here, it's simply with the amplifier. The way you do that is you put big capacitances on the bias voltages, okay, and that slows everything down. What I want to do is I want to derive this quantitatively, and then I want to stop, and I want to, we'll continue on with the beta multiplier next time. Before I do, are there any questions? Okay, so we only have, oh, I guess we have 9 minutes, I can do it. I want to take, whoops, shoot. I want to take and I want to talk about how you, because we'll see these self-bias circuits all the time in circuit design because they're really useful. So I want to show you how to look at the stability. And the way I'm going to do this is real feedback and control, is I'm going to break the loop. Oops, let's go with this color. I'm going to break the loop right here. And I'm going to inject a test voltage, and I'm not going to worry about the biasing. I'm going to assume everything's okay. And if I did this in a simulation just to prove it, I'd put a big capacitor here, and then I put a big inductor here to break, and it's in the questions. I get asked this all the time, so I put a question related to the book in the errata. So you put an inductor here, and it's effectively breaking the loop. None of the AC can feed back around. If I put a 100 Henry inductor here, none of that AC is going to feed back over here. And then I put a big capacitor here to feed the AC in. So for DC, the capacitor's out and the inductor's is short. Does everybody understand? So I've broken the loop, and then I inject this, and I'll call this V test. And then I look at the feedback around the loop. I'm going to call this V fed back. Does everybody see that? For a positive feedback is generally bad, and you've all heard like a microphone where you have positive feedback and you hear the screeching. However, positive feedback can be very useful if the loop gain is less than 1. because it dies out. You're feeding back a positive signal, but if it's 0.8 and then you amplify it again and it goes 0.64, 0.48, etc., it dies out, and the positive feedback circuit is stable. But the loop gain has to be less than 1. So if I apply a test voltage here, and I look at V fed back, what do I want V fed back over V test to be for this positive feedback circuit to be stable? Less than 1. Does everybody follow that? Okay, so I'm going to go ahead and write the circuit theory here. I'm going to call this VGS1. I'm going to say the current that flows there is ID, and I'm going to call this impedance here, or that voltage, Z times ID. So if it's purely resistive, Z is R. If it's resistor in parallel with the capacitor, it would be R in parallel with C. Any questions? Okay, so tell me if this is too sloppy. So I'll write V test is equal to VGS1 plus ID times Z. Do I need to write that out clear, or can everybody imagine that in their head? I think I need to write it out. I can tell. Okay, so let's write the circuit again. And what's the current flowing here? Well, I mean for AC. What did I just call it? ID. This is a real practical problem. So I write V test, this is VGS1, equals VGS1 plus ID times Z. Yay or nay? Okay, then would everybody be okay if I wrote that as ID times 1 over GM plus Z? Okay, so I want to speed things up. What is the current, what is the current flowing in there? ID. It's a current mirror. It's a trick. It's a current mirror, so what's the current flowing in there? ID. And so this is V fed back, but how is V fed back related to this transistor's VGS? Somebody's saying it. This voltage is V fed back. This voltage is VGS1, or VGS2 rather. Oops, I got those backwards. This would be 2. How is V fed back related to VGS2 or VGS1? They're the same. And how is VGS related to ID and GM? Let's call this GM1, and this would be GM2. Does everybody agree with that? Okay, but wait. This transistor has K times wider GM, and I know GM is equal to the square root of 2 times I times Kp times W over L, and GM2 is equal to the square root of 2I times Kp times W over L times K, because it's K times wider. So how is GM1 related to GM2? Right, square root of K. And then if I go back now and I plug this ID in here, and that's equal to V test, I'm sorry, V fed back, I get V fed back is equal to V test over 1 over GM2 plus Z times 1 over GM1. Does everybody agree with that? Okay, so but what is GM1 over GM2? whoops, V fed back over V test is equal to 1 over, if I multiply through here, what is GM1 over GM2? Yep, 1 over the square root of K. And what is, well, we'll just write this as Z times GM1. And I'm rushing it at the end, I apologize. But this Z ideally is 1 over R, or is R. The GM is 1 over R. This term becomes 1, and it becomes 1 over the square root of K plus 1. And you say, wait, that's always going to be less than 1, so it's always stable. Okay, but at high frequencies, if I put a capacitor here, what does Z become at high frequencies? So if I put a capacitance here because I bonded that out, what does that capacitance become at high frequencies? A short. If it becomes a short, this term goes to 0, and now, what happened? If K is 4, I get the gain is 2, and it becomes unstable. And I'm feeding around and adding. So does everybody follow that? Okay, so when we come back, what I want you to study, make sure you go over this and you ask questions because I rushed through that at the end. But when we come back, I want you to look at and know why we use this topology for the nanometer stuff. Okay, because the output resistance, it compensates for the output impedance. But read through to cascoding, and I'll probably, if we're lucky, we'll start cascoding. We definitely will have a quiz on Wednesday, and of course no class on Monday because of President's Day. Have a good weekend. Hope you have some fun doing your homework, that is.